In our previous lecture, we were discussing the convolution operation as part of the feature transformation stage that is shown here in this slide. After performing normalization and convolution, the next block in the single feature transformation stage is that of nonlinear mapping. This block is also known as the rectification stage. And in this block, the output coming from convolution is passed through a nonlinear function. For example, a rectified linear unit or through an ReLU function. The output of the nonlinear mapping goes to the stage which is known as the pooling stage. Pooling is needed for two purposes. Number one, it is used to reduce the spatial size of the representation, and that in turn reduces the number of parameters that are to be learned when we perform learning. It is also used to carry forward those locations in the representation where the convolution layer generates higher response. And that information could be valuable for some applications. There are two typical pooling schemes that are very popular. One is known as the max pooling and another is known as the average pooling. Let's look at these two schemes through the picture shown here. So let us say that we have a 4x4 image coming out of the convolution layer and after nonlinear mapping. Suppose we want to perform pooling over a mask of size 2x2. So what we will do is we will take our input to the pooling stage and divide it into number of regions such that each region is of the size that we have specified for our mask. So in this particular example, the 4x4 image will be divided into 4 2x2 masks or 4 2x2 regions or subregions. And in the case of max pooling, what we'll do is we will pick up the highest number from each of the subregions and use those numbers to represent the output of the pooling stage. In the case of average pooling, instead of picking the highest number, we'll take the average of the numbers over the mask and use that as the output of the pooling stage. So if you look at the numbers in this particular picture, for the leftmost mask, the four numbers are 12, 20, 8, and 2. So if we are using max pooling, 20 is the highest. So for these four numbers, we will use a single number, which is 20, to replace this 2x2 mask with a single number. And same thing will be done for the next 2x2 block consisting of 30, 0, 2, and 0. And in this case, this block will be represented by 30. And same thing goes for the other two remaining blocks. In the case of average pooling, instead of picking the highest number, we'll basically take the average over those four numbers in the mask and use that number as a representation. In any case, the end result of pooling in this case is that we started out with a 4x4 input to the pooling stage, and the output of the pooling stage now is 2x2. So basically what the pooling stage is doing is that it is reducing the size of the feature maps because convolution output is being viewed as consisting of features or a map of features. So what the pooling does is that it basically reduces the size of that map, and by doing so, the number of parameters that need to be learned in the deep learning network goes down. So that's the main advantage of pooling. Let's look at this slide. In this slide, what I'm doing is I'm showing you the results of these different stages of a single feature transformation stage. So let us say that input is consisting of this mandrel image that is shown at the bottom row. As a result of normalization, this image will go through certain changes, and the resulting normalized image is also shown here at this point. Once the image is normalized, it will go through a convolution operation. Of course, for the convolution operation, one needs to define or one needs to learn the weights that are part of the convolution mask or that are part of the convolution kernel. So in this particular case, I have taken a customized set of weight values that I have defined, and I'm using them to perform the convolution operation. So if I perform that operation, basically the result of that convolution is shown over here. Once the result of convolution is obtained, this is fed to the nonlinear mapping stage. So what the nonlinear mapping stage in this case is doing, it is an ReLU mapping. That means all the negative values will be converted to 0 and all the positive values will be linearly outputted as they are. So in this case, the output of the nonlinear mapping becomes this image where all the negative values that came out of the convolution operation have been set to 0. That's why this image is pretty dark. Now, this image goes into the pooling stage. And in this case, I'm using max pooling, and I'm using a mask size of 2 by 2 for pooling. So what happens is that this image gets divided into 2 by 2 blocks all over. And for every block, we pick a single number, which is the highest number for that block. And the resulting output of that operation is shown over here. So if you look at this output, you can see that this output is highlighting some of the characteristics that are present in the input image. So basically, you can say that some kind of feature extraction has been performed. And typically, in deep learning networks, you will not have a single feature transformation stage, but you will be using several such filters to extract multiple features. So that way, you will be able to extract number of attributes, a number of properties, or number of features from the input image. And of course, these features will be learned specific to the task that you want to perform. So that's the basic idea of single feature transformation stage. Now, when you perform convolution, you will come across number of terms, or you can say the parameters that are involved in performing these convolution operations. So one of that parameters is known as the stride. The term stride determines how the convolution mask is moved during the convolution operation. One can imagine the mask being moved continuously. That is, suppose you have a 3 by 3 mask, so you place it at the starting location and then you move it by 1 pixel to the right, because it's a 3 by 3 mask, so you just move it 1 pixel, and that way you will have a new center for the mask, which will be adjacent to the previous center of the mask, and you keep doing till you reach the end of the row, and then you move 1 pixel down and go back to the left of the image and again repeat this operation. So if you don't move by 1 pixel or don't move to the next center of the convolution mask, which is just adjacent to the current center, but you move it with certain different amount, then that amount is what we call as the stride. So the stride value of 1 is the default setting in the convolution operation in PyTorch. But if you want to use something different, then you will have to specify what stride value that you want to use. To get a clear picture, let's look at this figure shown in this slide. So if you look at the blue cells, those blue cells show the positions where a 3x3 mask would be placed with the default stride value of 1. And if you want to use something different for a stride value, for example, let us say the value of 2, then the mask will not be placed in all the blue cells, but it will skip one blue cell in between. So all the cells marked with X's show where the mask will be placed. Now obviously you can see that when you are using a stride value of 2, you are calculating the convolution result at fewer locations. So what the stride does is that, number one, it reduces the size of the convolution feature map that you will get out of the convolution operation. And this reduction in size is often termed as downsampling. So you will hear people saying we are doing downsampling the image by using a stride of 2 or 4 or whatever number they want to use. So that's the meaning of downsampling. Another term that you will come across in convolution operation is what we call as the dilation. The term dilation of the convolution mask is used to effectively enlarge the mask so that convolution is applied over a larger area. Now this is different from using a larger or a bigger kernel mask to start with. To understand the difference between using a larger mask and using dilation to effectively enlarge the mask, let's look at the picture shown here. So if you look at the left-hand image consisting of A, B, C, D, E, F, G, H, I. So that's a 3x3 mask of original size. And when we apply this mask over an image, we'll be basically looking at continuous underlying pixel values to calculate the convolution result. But if we want to use a dilation operation along with the convolution mask, then we will be skipping pixels in between when we are calculating the output of the convolution operation. So if you look at the right hand side picture, that is showing the blue cells which correspond to the underlying image pixels, where the values of those pixels will be taken and multiplied with the weights of the convolution mask, while the white cells are those underlying image pixel values that will not be part of the convolution operation. That is, those values will be ignored. So effectively, what we are doing is we are calculating the convolution operation over a 5x5 area when the size of the convolution mask that we are using is 3x3. It is different from using a convolution mask of 5x5, because if we were using a convolution mask of 5x5, then we will be taking into account all the underlying pixels that are below this mask in the given image. Now it turns out that this dilation operation is useful in some of the applications to highlight some of the characteristics that are needed for those applications. Now with those definitions, let's move on and look at CNN terminology. Once again, some of the terms that you're going to be coming across. So there is a terminology, or there is a term that you will be coming across. This is known as the local receptive field. This local receptive field term refers to the two-dimensional arrangement of neurons in the input layer. So at the input layer, you can assume an arrangement of neurons in a two-dimensional fashion, and that is what we refer to as a local receptive field. Stride is already explained in the previous slides. All right. So when you are performing the convolution operation, let us say you are using a 5 by 5 convolution mask. So what we will do is you will assume that these input neurons are capturing 5 by 5 pixel values, and through convolution the result is being calculated, being rectified, going through pooling. Then that result basically comes and sits in the first hidden layer or in the next stage of the deep learning network. Another idea or another term that you need to understand is locality and translation invariance. Remember, the convolution mask is much smaller than the image to which the operation is applied. So as we have seen before, the mask is moved over the image. Now the reason behind moving the mask and not using a mask of the same size as that of the image is that what we want to do is we are assuming that the objects that we are trying to capture or recognize are of a smaller size than the image. So these objects could be present anywhere in the image. As shown in this particular picture, for example, look at that bird. This bird could be in the top left corner of the image, could be in the center of the image, it could be at the bottom right corner of the image. So what we want to do is we want to be able to have a mask of a reasonable size, and that mask will be moved over the image step by step from left to right and then going down, so that through mask we will basically scan the entire image, and at different positions of the mask we will be capturing the underlying features or characteristics of the image. And this is done basically to make sure that your system is not affected by the location or translation of the objects present in the images. The same concept of locality and translation invariance is shown in this slide. That is what we don't want. We don't want a mask of size which covers the entire image. We rather have a mask of a smaller size that we move over the image, then we move over the image, and then we move over the image. All right, so let's continue with the CNN terminology, and let us say that we have an input image consisting of 28 by 28 pixels. So you can say that that basically is the image being fed to the input neurons or to the input of the network. And somebody says, well, the hidden layer or the first hidden layer, they assume that there are a number of hidden layers in the network. So the first hidden layer has 3 layers of 24 by 24 neurons. So if we look at this picture, what does this picture tell us? This picture tells us that we have 3 feature maps that are present in the hidden layer or that are being learned or figured out through our convolution operation. And each feature map, of course, corresponds to a different convolution mask or different convolution filter. And of course, the weights of that mask or filter will be learned during the learning stage of the system. Another thing we can note from this picture is the size of the kernel masks. See, the input image is 28 by 28. The hidden layer size is 24 by 24. That means the hidden layer size is 4 pixels less than the input size. Now remember, the convolution mask, if we do not do the padding of the input, then the output of the convolution mask will be smaller than the input image. And the reduction in the size depends on the size of the convolution mask. So in this case, if the input is 28 by 28 and the output of the convolution layer or the hidden layer size is 24 by 24, which means we have shaved off 2 pixels on the top, 2 pixels on the bottom, 2 pixels on the left, and 2 pixels on the right. And that's how we are getting 24 by 24. And shaving off 2 pixels means that our mask size is actually 2 plus 2 plus 1, where 1 is coming for the center of the mask. So mask size is 5 by 5. So in this case, by simply looking at this picture, we can say that this picture or this network is using 3 kernel masks or 3 filters. Each filter is of size 5 by 5 to produce the output for the first hidden layer, which consists of 3 planes of 24 by 24 neurons or 3 feature maps of size 24 by 24. Now, oftentimes you may want to visualize how do the how do the kernel weights look like. So one way of doing the visualization is that once the network has been trained, you can read out or you can extract the weights corresponding to different masks, and then using those weights you can generate some kind of images that show you how the mask looks like. So in this particular case, we are showing you 20 different images corresponding to 20 different feature maps or filters or kernels. And in this case, each map or each kernel is of size 5 by 5, indicating that the filters are of size 5 by 5 and the shades in these pictures represent give you an idea of the weights of these filters. Whiter means more negative values and darker means more positive values. So oftentimes that is what one can do. So here is a very simple convolutional neural network example, just the architecture, not the actual weight values and anything. So you can say that input layer consists of a 28 by 28 neurons. So that's where you will feed an 28 by 28 image. Then the hidden layer consists of 3 planes or 3 feature maps. And of course, the size is 24 by 24, which means what we are doing is we are using here 5 by 5 filters to come to these 3 feature maps. Now, if you look at the pooling stage or the output of the pooling, we are showing it as 3 times 12 by 12. That means the number of feature maps remains the same, but the size of the feature map has been reduced from 24 by 24 to 12 by 12, which tells you that the pooling mask size is 2 by 2, because if we use a pooling mask size of 2 by 2, we will be basically dividing our feature map by a factor of 2 in both the directions x and y. So 24 by 24 will become actually 12 by 12. Now, if you do not want to extract any more features, so at this stage you can say we have 12 by 3 times 12 times 12, So that means 512 features that have been extracted. And what one can do is one can feed these features to a multi-layer perceptron network or to a support vector machine or to a logistic regression classifier and perform the image classification task. But before we feed these features to a logistic regression or a multi-layer perceptron network, what we need to do is we need to take this output of the pooling layer, which is shown here in the form of 3 different planes of size 12 by 12, convert that into a flat representation of 512 numbers. So that will be another mapping that will be involved, and then this output can be fed to a support vector machine or any other classifier that you want to use to perform the classification. So what we have done up to this point over here is that the feature extraction has been done, and this feature extraction will be, of course, done automatically through back propagation algorithm, which will of course be coming here once you have the multi-layer perceptron or any other stage. Then whole thing can be learned by itself through a collection of training examples. Here is another slide to give you a little bit more idea of what is involved in the convolution stage. So basically you can say that here is the input image, and you have a number of filters. So these are what you can call as filter banks. So basically this image is convolved through these with all these filters, and for every filter it produces a feature map. So if the number of filters is 10, we will get 10 feature maps, and this information or these feature maps are then rectified, and oftentimes another normalization is performed, which is known as the contrast normalization, and that output is kind of shown over here, and this output is then sent to the pooling layer where the pooling is performed. So basically this is the output of the convolution stage that you can say will be coming out, and it consists of 2 main components, convolution and pooling. And in the pooling layer, as we saw earlier, basically you will be taking different masks, or you will be grouping your convolution layer output into smaller groups of pixels, and for every such group you will be calculating either the maximum value or the average value, etc., etc. And this formula tells you the relationship between the convolution filter size with the stride 1 and the size of the pooling mask, which is P by P. Then what will be the result of final output after performing pooling. Here is a specification for the convolution layer in Torch or in the NN module of Torch or PyTorch. So basically, if you look at this specification, you need to specify how many channels are there in the input image. For example, if it is a color image, you will have 3 channels, RGB. If it is a gray level image, then of course the number of channels is 1, or you might have many more channels if it is an intermediate stage in a network. In that case, the output from the previous stage will be the input to the convolution layer. So you need to specify how many channels, and this has to be an integer specification. You need to specify how many output channels are there. That is your convolution operation or convolution layer actually, how many output maps or feature maps it's going to produce. You need to specify what is the size of the kernel. You specify what is the stride. You specify whether you want to do any padding or not. You specify whether you want to do any dilation or not. So remember, we have discussed all these specifications or all these parameters. Then you need to specify what we call as groups. Groups basically is a parameter that I'm going to discuss little later, but it basically tells you how many inputs and how many outputs and what is their relationship. So we'll come to that towards the end of this presentation. And bias is basically similar to the bias term in our neuron models. Whether you want to have a bias or not, that is what is specified by the bias. So if you have the bias value will be taken as 1 and the corresponding weight value will be learned. If you don't want to have any bias, then obviously the bias value will be taken as 0. So that's basically how a convolution layer in Torch is specified. This is the specification for specifying a pooling layer in the Torch. And as I said, there are different ways of pooling. So this specification is showing you how you will specify max pooling. So again, you can see that it is asking you to specify the size of the pooling window or pooling mask. So that will be kernel size, whether you want to have any stride or not. So again, same concept, padding, dilation, and return indices, if true, will return the max indices along with the output. Remember, I mentioned that sometimes you not only want the max value, but you also want to know where that max value occurred. So this parameter controls that information. And of course, ceiling mode is another parameter. When true, we'll use ceiling instead of floor to compute the output shape. So with that, let's look at an illustration of convolution layer. So I'm going to go through some of the steps, or I'm going to show you some of the results corresponding to different parameter choices. So we will do the illustration using an image that is shown here, and this image is of size 235 times 180, and of course it has 3 channels because it's a color image. I'm going to implement 4 filters. Those are pictorially shown here, and you can see that filter 2, 3, and 4 are really nothing but similar to filter 1, except that in one case it's an mirror image, in another case it has been rotated, and again another image. So basically we have 4 filters, and these are 5 by 5 filters. And if you look at the array values for these filters, so the filter values are -1, which is shown as most negative or black, then -0.5, kind of dark red, 0, 0.5, and 1. And those are the values that keep on repeating. And we are going to be using 2 layers of convolution. That means we'll do the convolution in the first layer, and after rectification and pooling, whatever results we get, that information or those maps will be fed to the second layer. And second layer will again use the same set of filter masks that we are showing you here. And if you want to read about this whole thing, this is the link to a website where you can actually read in details and look at the code also that has been used to perform or to do this visualization. So here are some convolution results. So if you look at the top row, this is showing you the results before rectification. And there are 4 filters. So obviously we got 4 output images here. So those are the shown corresponding to 4 different filters. And the bottom row is the result of first layer of convolution after rectification. So what we have done is we have taken all the negative values and they have been set to 0 because we are using ReLU, and positive values have not been disturbed. So if you rectify the output and then show it or display it, this is what you will see as shown here. And as you can see here in these images, we are able to get some characteristics or some areas of the images which have been highlighted here. And the basic idea is that some of these areas might be of use for object recognition. Of course, in this case, the filters are not learned, but they have been customized. So you may not be getting all the characteristics that we really want to extract from these from this input. But this is only for illustration purposes. So if we take the output of the first stage of convolution after pooling and feed that output to the next round of convolution where we are using the same set of filters. So basically, again, the top row shows you the output before rectification. The bottom row shows you the output after rectification. So you can see at the bottom row that the output now is kind of highlighting some of the image features as eyes or short line segments, etc. in this output, which means we are extracting some of the features from the given image. And obviously, as I mentioned earlier, if you had many filters and these filters were trained to extract certain important features, then obviously we will see a lot more features in these images. So in this case, you can say that we have 4 feature maps, and those are present at the bottom of this slide. Another thing to note here is the size of the filtered maps. So you can see here the size is in terms of along this direction, you have about 80 columns, and in this direction you have about maybe 110 rows and 80 columns. So obviously the size of the output at this stage is smaller than the input image, which was almost twice of this size, and that's because of the pooling done at the first stage, as well as because of the, not doing any padding. So every time you do convolution, the size is reduced a little bit by the half of the number of pixels equal to the mask size. So in this case, since we are using 5 by 5 mask, so on all the sides of an image, we will be chopping off 2 by 2 pixels, 2 top rows, 2 bottom rows, 2 leftmost columns, 2 rightmost columns. So that's how the result is reduced. Now let's look at the effect of stride parameter. So if I take the second layer and in that convolution specification I introduce the stride parameter, that means we will be skipping certain pixels or certain locations as we apply the convolution mask, which means that the size of the output map will be much smaller, and that is what you can see here. Now we have a much smaller size at the output of the second convolution stage because of the use of stride parameter. This slide shows you the effect of dilation, and in this case we are using a dilation value of 3. And we are showing the result at the first layer before and after rectification, but dilation is being performed on the first layer. So you can see that in this case the image features appear prominently compared to the output without dilation that we had seen earlier. So dilation does bring out features more prominently. The previous slide showed you the output of the convolution layer using the filters that were basically customized, and those customized values had no relationship with the features we wanted to extract or the classification task we wanted to perform. Here is an illustration of output from different convolution masks taken from a trained convolutional neural network which has been trained to perform a certain classification task. So in this case, what we are showing you is the result for one particular image. So this is the input image, and we have 6 filters, and the output that is being shown is after the ReLU nonlinearity. That is, this image is convolved with these filters, and the output of the filters is fed to the rectification unit, and whatever output you get from the rectification, that is being displayed. So you can see that if you look into these pictures, each filter is capturing certain elements of the input image. And together, these filters can provide you a lot more information about what is present in the image. And of course, in practice, instead of using 6 filters, typically 16, 32, 64, or even 96 filters are used. That means we are able to extract all kinds of characteristics, or we are able to make that many filters learn about all kinds of characteristics in the images so that one can perform classification. There is another convolution operation that is quite confusing and sometimes tricky to understand. It is known as one-by-one convolution. Now you might say, what's the point of having a one-by-one convolution? Basically, if I apply a one-by-one convolution to an image, all it is going to do is it's going to scale up or scale down the pixel values. For example, if the convolution mask has a value of 0.5, then all pixel values will be scaled down by half, because that's all a one-by-one convolution can do. So you might wonder, why talk about such a convolution? It turns out that one-by-one convolution has many uses, and to understand it, let's not look at a single image, but let's look at m channels of inputs. So suppose you have m planes of images or m inputs, and what you want to do is you want to apply one-by-one convolution to this input, and you want to get a single output of this convolution operation. Since you have m input images, for each image you will need its own one-by-one convolution operation. That means you need to specify m different weights, one per one-by-one convolution. And of course, convolution will be done pixel by pixel. And in this case, if you look at this location K, where you want to calculate the result in the output layer of this one-by-one convolution, then essentially you look at all pixels lying at the location K in each of these input images. And what you are doing is, through one-by-one convolution, each of these is being multiplied by the corresponding weight, and then you are adding them up to produce the output. So essentially, the formula for the output of the one-by-one convolution in this case can be written as this. That means if I apply one-by-one convolution to these m input channels, ultimately the output will be a single feature map whose size will be same as the size of the input images, because in this case there is no need for padding and there is no cropping that is going to take place. So basically output will be a feature map of the same size as the input image size, and this feature map at different locations will have its values governed by this formula that is shown here. So that's really what is going on in 1-by-1 convolution. You might still say, well, that's fine, but why use 1-by-1 convolution? It turns out that 1-by-1 convolution can be useful to do a reduction in the size of the parameters, or to do what you can call as a dimensionality reduction. So to see how that works, let us look at a situation where we have 64 filtered images or feature maps, and let us say that each map is of size 28 by 28. And suppose we want to apply 16 different convolution masks, and let us say that these masks are all of size 3 by 3. So you have 64 filtered images. Each image is of size 28 by 28. So typically this will be at some intermediate stage in a deep learning network. And what we want to do is we want to apply 16 different filters or 16 different convolution operations or masks of size 3 by 3 to these images. So if you look at how many operations are involved, you will find that the number of operations is given by 28 times 28 times 16 times 3 times 3 times 64. And that turns out to be 7225344 operations. Now let's look at another way of doing the same thing. Instead of directly applying 16 3 by 3 masks on 64 channels of incoming images, what we do is we first reshape the incoming images to size 28 by 28 by 4, and we do that using 4 1-by-1 convolution filters. So that operation is going to require 28 times 28 times 4 times 1 times 1 times 64. So that is 20704 operations. And next we apply 16 3 by 3 filters on the reshaped output, and that is going to need 28 times 28 times 4 times 3 times 3 times 16 operations. So if we add up these two operations and compare them with the original number of operations, we'll see that we require 90% fewer operations. That means 1-by-1 convolution is able to save us a lot of operations. That means this allows us to speed up the training of a deep learning neural network, which is generally very, very time consuming. So that's the reason 1-by-1 convolution is popular and used for doing these kinds of things. Here is a 1-by-1 convolution illustration for the running example that we have been using. So in our example, we had 4 output maps coming out of the convolution layer. So what we can do is we can take those 4 maps and we can apply 1-by-1 convolution, and that will basically convert those 4 maps into a single convolution, into a single map or single representation. So in this case, that is what is being shown. And for those 4 maps, the corresponding 1-by-1 mask weights are 1.0, 0.5, 0.25, and minus 1.0. These numbers were chosen just arbitrarily for the illustration purposes. All right. So the right image is after rectification and the left image is before rectification. So the main thing about 1 by 1 to remember is that 1 by 1 convolution allows us to reduce the dimensionality while retaining the features of the input images. So that's the most important characteristic or advantage of using 1 by 1 convolution. Now let's take a brief look at groups parameters, which I mentioned earlier as part of the specification for a convolution layer operation. So this parameter controls the connections between the input and output channels. So groups equal to 1 is the default setting. So if you don't specify any number for groups parameter, equal to 1 will be taken as the default setting. And what this setting really means is that if, for example, in the specification that is shown here, you have 3 input channels, you have 3 output channels, you have a kernel size of 5, and you are not using any bias. So basically what it is telling the system to do is that the input image has 3 channels and you have 3 output channels, and basically you are going to be using 3 filters as shown here, or 3 sets of filters I should say, because each filter over here basically contains a mask for the red channel, a mask for the green channel, and a mask for the blue channel. So basically when you have some arrangement like this, which is the most common arrangement, we say that we are using groups equal to 1 as the setting. Sometimes you want to use a different setting for the groups parameter that is not equal to 1. It has to be an integer number, all right? So consider the case where the number of input channels is more than the output channels. And let us take a look at this example over here. So we have 8 input channels, we have 4 output channels, and let us say that we specify groups value equal to 4. Kernel size is 5 and bias is false. Now the groups value has to be an integer number, and this integer number has to be a number such that it should be able to divide both the number of input channels and the number of output channels. So in this case, the number of input channels is 8, which is divisible by 4. The number of output channels is 4, which is also divisible by 4. So if we give this specification for the convolution layer, what we are telling or what we are setting up is an arrangement like this. That is, a group value equal to 4 in this case allows us to create multiple paths where each path connects only a subset of input channels to the output channels. So you can see that these inputs are only affecting this one. These inputs are basically connected over here and so on. For other settings of groups parameter, again, you can go and take a look at this blog posting that I did last year and see how different values for groups parameters affect the connections between the input and the output of the convolution layer. So we are going to stop here. And what is coming next is, in the next lecture, we are going to be looking at some well-known CNN architectures, beginning with the LeNet, which is considered the first convolutional neural network. Thank you.